We're going to go over section 5.4, and we're going to solve systems using an augmented matrices and row operation. So this is something we actually did last year in secondary one. So hopefully after this video, you feel like this is kind of reviewed and kind of got back in your head before we do some bigger systems. So before we do this, let's start with our warm up. We've got three matrices, matrix A, B, and C, and we want to do some matrix operations. So let's start with number one, matrix A plus matrix B. So remember, when we're adding matrices with the same dimensions, so all of these matrices have 2 rows and 2 columns. When we're adding and subtracting the same dimensions, our answer should also be those same dimensions. So 2 by 2, we know should be our solution. We add corresponding elements. So when I'm thinking of A, I like to start in this top upper corner, and I'm going to combine that with the corresponding element in B. So 4 plus -3 is 1. And then I like to work across in the row. So I would go to 6 and 4, those corresponding elements, and add those together. Once that whole row is finished, I go to my second row, so -1 plus 7. And last 0 plus 1. So this would be the solution, the resultant, as we call it in matrices, for matrix A plus matrix B. Subtraction can be a little trickier, so we want to make sure we're thinking, especially if we are subtracting negatives. So again, we know my answer is going to be 2 by 2 because both of my matrices are 2 by 2. So I'm going to start with matrix C because it says C minus B. I'm going to take those corresponding elements. So 6 minus -3. I know subtracting a negative is really adding, so there's 9. My next row or next element in my row is 2. 2 plus 4 is 6. Now I can go to my next row, 8 plus 7, so that's 15. Whoops, 8 plus 7, not 8 minus 7. It should be 8 minus 7. Excuse me, that's 1. And then 2 minus 1 is also 1. So subtracting those 2 by 2s, we end up with this matrix. And last, we want to do a little bit of a scalar first. So we want to do 2 times matrix A first. So I'm going to think about writing this one out. If I take this matrix A and I multiply everything in here by 2, I end up with, 2 times 4 is 8. 2 times 6 is 12. 2 times -1 is -2. And 2 times 0 is 0. And now I want to add that to matrix C. And I'll just rewrite that since I wrote 2 times A. So now I want to add those corresponding elements. So 8 and 6, 12 and 2, -2 and 8, and 0 and 2. So when we scale, we probably may benefit from doing a little bit more work. Try not to keep too much of it in our heads. So let's go ahead and jump down below here and let's get started solving these 2 by 2s. So it says that a system of linear equations can be represented, remember we have this vocabulary word, by an augmented matrix. So this is a matrix that stores the coefficients and the constants of a linear system. And we're going to use row operations to help us solve this. So let's just remind ourselves, if we have this linear system here, x plus 3y equals 5 and 2x minus y equals 3, I can write an augmented matrix, which has our bracket, and I can take the coefficients and the constants from each of these equations. So for my first equation, remember there is a 1 in front of that x, so the coefficient 1. The coefficient from y is a +3. We don't write an equal sign. Remember, we write a vertical or draw a vertical line, and we put that constant 5 on the other side. And then we do something similar for our next equation. We want to make sure we're taking our coefficient, so 2. Y has a -1 in front, and it's equal to a 3. So we would call this right here, these 4 terms, this is our coefficients. This is that coefficient piece of the matrix. And our 5, 3 here would be our constants. So our goal today is going to be to change those coefficients, and we'll talk about the pattern in just a second. So let's go down below in this box here. It says that when we're working with augmented matrices, remember there's only 3 operations that we can do. Number 1, we can interchange 2 rows, which we would call that a row swap. We can, number 2, reduce a row by a non-zero multiple of that row. So we don't want to multiply by 0. That just wipes out a whole row. So we're not going to do that. We need to multiply by a non-zero number. And number 3, we can replace a row by the sum of that row and a constant multiple of another. So we can multiply a row and add it to something else. So these are our only 3 options. And to kind of help us keep track of that, we've got some shorthand. And we did use this last year in secondary 1, but let's review a little bit. So we're going to refer to rows with capital R. So our first thing here is we're going to number the rows. So we're going to have row 1 and row 2 today. When we swap rows, if we want to swap the positions of row 1 and row 2, we're going to use this notation with this double-sided arrow. This is going to show that we want to switch those places. When we multiply a row by a constant, like 4, we would show that notation 4 times R sub 1, row 1. And last thing, which has a couple of operations, if we need to multiply a row by a constant like -2, we can add it to another row and add it to another row. We're going to see notation like this. We're going to state which row we're multiplying to. So -2 would be multiplied to row 2. And then we're going to add it to row 1. And it says, well, no, the last row is in the operation is the row that will change. So for this example we were just talking about, we would be talking about row 1. This row 1, because it's written last in this statement, this is the row that will change. So I'm going to say this will change. So we'll remind ourselves what that looks like in just a second. So before we solve some systems, let's just practice a little bit with this notation. So let's look at example 1. It says to carry out the indicated row operation and write the new augmented matrix. So we're not solving here. We're just going to practice some of this notation, this shorthand. So as we look at problem A, I can see my system, 3x minus 9y equals -9, and I see 2x minus 5y equals -4. So I can kind of work backwards. And my shorthand is telling me to take 1/3 of row 1. So I'm not going to be changing row 2 at all. So when I do these, a lot of times I will rewrite the row that's not going to be changed in that step. So for this first problem, I'm not changing row 2. I'm just going to change row 1. So I rewrote row 2. But I am going to take 1/3, so you can kind of write it by here if you'd like to, and I need to multiply that whole row by that. So 1/3 times 3, 1/3 times -9, and 1/3 times -9. So we've performed our row operation. We scaled one equation by 1/3. Let's look at problem B. Again, we've got our 2 equations, and this time it wants us to take -2 and multiply it to row 2. So I want to multiply this whole row 2 by -2. And then I want to add it to row 1. Now remember, this is the one that's going to actually change, this row 1. So I'm just using this row 2. I say that a lot. I'm just going to use this row 2 to help me change row 1. So I'm going to rewrite row 2 because it's not actually going to change. I'm just going to be changing row 1. So let's multiply first. So -2 times +2, so that would be a -4. -2 times 5, so that's 10. And -2 times -4 is 8. So I'm going to use those new values and I'm going to add them to the numbers that are in row 1. So -4 plus 1 is -3, and I'm going to put that in my first spot. 10 plus negative 3 would be a positive 7. And 8 plus negative 3 is a positive 5. So we took 2 times that second row, those values, and combined them with the values in row 1. So we didn't really change the second row. We just used it to help us change the first row. So let's try it again on problem C. This time I want to do 3 times row 2, and I want to combine it to row 1. So again, this is the row that's going to actually change, this row 1. So I am not going to change that second row, so I'm going to rewrite that first. So let's take 3 times row 2. 3 times 0 is 0. 3 times 1 is 3. And 3 times 2 is 6. And those values need to be combined to the values in row 1. 0 times 1 is 1, or 0 plus 1 is 1, excuse me. 3 plus negative 3 is 0. And 6 plus negative 3 is positive 3. So we took 3 times row 2 and used those numbers to help combine with row 1. So let's look at what we're going to be using these row operations to help us find. So in this box below, it says that to solve an augmented matrix, we're going to use row operations to change that coefficient matrix, so we saw that at the top, to the identity matrix. And remember, the identity matrix has 1s in the main diagonal and 0s everywhere else. So as we look at this example below, this main diagonal, the identity matrix, will always have 1s, and there's going to be 0s everywhere else. So the way this is written right now, this 1 is in the x spot. X would be equal to A, whatever value that is. And in my second row, we have a 1 in the y spot. Y is equal to B. So we would have our solution to our system once we have this matrix. Now there is kind of a pattern. We want to get this in a certain order. So this is what we're going to practice. We're going to get this position always first. I want to have a 1 in this first row and first column always. So I'm going to get that 1 first. And then I'm going to work in a column. Once I've got the 1 in the column, I want to get the 0 in the column. So I would like to get this position to be a 0, and I'm going to do that second. And then I want to go to my next column, but I want to make the 1 first. So in my second column, my 1 is in this second row, and I want to get this value third. That's the third thing I'm going to work on. And lastly, once I've got the 1 in the column, then I need to make this value a 0. So we're going to work around kind of in a circle, starting with a 1 and then creating a 0 in that column. And then we'll go to our second column and create the 1. And last, we'll create the 0 in the second column. And then we'll have our solution to our system. So let's turn our notes over to the back page and let's try. So example 2 says to solve this system using an augmented matrix, and we're going to show our row operations. So I want you to be able to show the shorthand notation for every step as you solve. So as we're looking at this first equation, I know that I'm looking for that identity matrix. I need the 2 right here, this position, to become a 1. Now I have 2 options. I could multiply 2 by 1/2, and that would give me 1. Or I notice that there is a 1 in this row down below, and I could just switch these 2 equations and my 1 would be in this 2 spots. I'm going to go ahead and switch my rows. Would you please use your notation? I would like to take row 1 and switch it, so we've got our double-sided arrow, with row 2. So you're going to show me what you're about to do. So I'm about to switch my rows. So here's my second step. My second row is going to become my first, and my first row is going to become my second. I'm just swapping those 2 rows. Now I've got my 1 in that top position. So in my column, once I have my 1, I want to create a 0, and right now I have a 2. The only way we create zeros is multiplying the 1 by the opposite, in this case of 2. Well, the opposite of 2 is negative 2. And I'm going to multiply that to row 1. But I need the 0 to be in row 2. So I need my answer to be in row 2. Now remember, whatever's written second, whatever's this plus, this is the row that's going to change. So I know my first row is not going to change. I'm going to use it to help me change the second row. So we're going to take the first row and we're going to multiply that by a negative 2. Negative 2 times 1 is negative 2. Negative 2 times 3 is negative 6. And negative 2 times 5 is negative 10. Those values I now need to combine with the values in my second row. Negative 2 plus 2 is 0. I wanted that 0, so that's good that that happened. Negative 6 plus negative 1 is negative 7. And negative 10 plus 3 is also a negative 7. We are halfway finished with this matrix, solving this matrix, because our first column is finished. We got our 1 and then we got our 0. So now we're ready to go to our second column. I always want to create the 1 in my column first. And the 1 needs to be in the place that this negative 7 is. To create a 1, we want to scale a row. And we scale a row by a reciprocal. The reciprocal of negative 7 is negative 1/7. And if I multiply negative 1/7 to row 2, this negative 7 will become a 1. And I need that to happen. So for my next step, again, I'm not going to be changing the first row. I'm just going to scale the second row, and that's going to give me my 1. So my whole second row gets to be multiplied by this negative 1/7. Well, negative 1/7 times 0 is still 0. Negative 1/7 times negative 7 is 1, which is what I wanted. And nicely, negative 1/7 times that second negative 7 is also a 1. Last thing I need to do in my column, once I've got my 1, is I need to create my zeros. So I need this 3 to become a 0. In order to create zeros, I have to multiply the 1 in the column by the opposite of my number. The opposite of 3 is negative 3. I need to multiply the row 2 by a negative 3 so that I can combine it with row 1 to get my 0. So again, remember that row 1 is the one that's changing. So that's why it's written second. So in my next step, I know I'm not changing row 2. So I'm going to write it first. But I am going to change row 1. And I'm going to change row 1 by multiplying this second row, by negative 3 and adding it. So negative 3 times 0 is still 0. Negative 3 times 1 is negative 3. And negative 3 times 1 is negative 3. So those values I'm going to combine with the row 1 values. 0 plus 1 is still 1. Negative 3 plus 3 is 0. So we wanted that. And negative 3 plus 5 is a positive 2. I know I'm finished because I see that identity matrix now. And I have one x that is equal to 2. And I have one y that's equal to 1. The solution to a system is always an ordered pair. The x value, comma, the y value. So we always want to write that with an ordered pair. So let's try again in example 2. This time we're starting with systems that are written not as an augmented matrix. So that's the first thing we're going to want to do, is write them as an augmented matrix. And then we will use our row operations to solve. So I'm going to start with problem A, and I'm going to take my coefficients from my first equation. The coefficient on x is 1, the coefficient on y is 2, and my constant 4. My second equation, I also have a coefficient of 1 on my x. My y is a 1/2, and my constant is 4. So I love when this happens, that my first element that I need to be a 1 is already a 1. So that's already cut off one step in my process. So now that I have my 1, I need to create the 0. In order to create a 0, I have to multiply my 1 by the opposite of what I want to become a 0. The opposite of 1 is negative 1. So I need to multiply the first row by a negative 1, and I'm going to combine that to row 2. So row 2 is the one that's changing, not row 1. So I'm going to rewrite row 1. And I'm going to take that negative and I'm going to multiply by negative 1 that entire row and use those values to combine with row 2. So negative 1 plus 1, 0. Negative 2 plus 3/2 is negative 1.5, but I would suggest that you write this as a fraction, negative 3 over 2. It'll help when we go to our next step. And then negative 4 plus 4 is 0. So we got our 1 that came within the problem this time. After we had our 1, we created our 0. And now we're ready to make this negative 3/2 into a 1. We know to create a 1, we have to multiply by the reciprocal. And the reciprocal of negative 3 over 2 is negative 2 over 3. So this is why it was better to leave that as a improper fraction, because now we need to multiply by a reciprocal. So I'm not going to change that first row again. So I'm going to go ahead and rewrite that. But I do need to scale the whole second row. Negative 2/3 times 0, still 0. Negative 2/3 times negative 3/2, there's the 1. And negative 2/3 times 0, we have 0. So lastly, once we've got our 1, we need to create our 0. So this 2 needs to become a 0. So I need to multiply the 1 in that column by the opposite of 2. The opposite of 2 is negative 2. I'm going to multiply negative 2 to row 2. That's where my 1 is. And then I'll add those values to row 1. So row 1 is the one that's going to change. So I'm not really going to be changing the second row. I'm just going to use it to help me change that first row. So I'm multiplying this second row by negative 2. So negative 2 times 0 is 0. Negative 2 times 1 is negative 2. And negative 2 times 0 is 0. So now those values are going to be combined to row 1. 0 plus 1 is 1. Negative 2 plus 2 is 0. And 0 plus 4 is 4. So once we see that identity matrix, we now have our solution. X is equal to 4 and Y is equal to 0. We have our ordered pair. This is where these two equations would intersect. So it's really nice when we can start with a 1 in that top corner. That made that a little bit shorter. All right, let's try B. Problem B, again, we want to set up in our augmented matrix first. We have a coefficient of 10, negative 2, and then we have our constant, a positive 6. Our next equation, our coefficient for x is negative 5, for y is a positive 1, and we have our constant, negative 3. Now this time, unfortunately, we do not have a 1 in that upper spot. That 10 we want to change to a 1. So I'm going to multiply by a reciprocal. The reciprocal of 10 is 1/10. And if I multiply row 1 by 1/10, this 10 will become a 1. So I will not be changing the second row. So I'm going to rewrite that. But the whole top row needs to be multiplied by 1/10. And I would like to simplify fractions as we go. So negative or positive 1/10 times 10, so that's 1. 1/10 times negative 2, so that would be negative 2 over 10, which simplifies to negative 1/5. 1 over 10 times 6, that would be 6 over 10. 6 over 10, they simplifies to 3 over 5. We now have our 1, so we need to create in the column a 0. So this negative 5 needs to become a 0. The only way we get 0 is multiplying that 1 by the opposite. So we need to multiply by the opposite of negative 5, which is 5. We need to multiply it to row 1 because that's where our 1 is. and then we'll need to add it to row 2. So row 2 is what is changing. So I'm going to rewrite my first row because it is not going to change. I'm just going to use it to help me change that second row. So I need to multiply my first row by 5. 5 times 1 is 5. 5 times negative 1/5, so that would be negative 1. And 5 times 3/5, so those 5s would simplify, which would leave us with a 3. So now we need to combine 5 plus negative 5, 0. 5 times negative 1, negative 1 plus 1 is 0. 3 plus negative 3 is also 0. So remember, we've kind of got an interesting situation here. We now have a whole row of zeros. When our variables eliminate, we have to look at what is left. Our variables have eliminated here on the bottom, and we're left with this statement that 0 equals 0, which is a true statement, which in any system, if we have a true statement once our variables are gone, this means that there are infinitely many solutions. So we'll want to watch if that second row goes to all zeros, then we'll have infinitely many solutions. Let's try one more. Let's look at problem C. A difference in problem C, this is not quite in an order yet to set up as an augmented matrix. So I do want my augmented matrices to go X, Y, and constant. So my second equation has to change a little bit. So we need to change the order for this second equation. Let's go ahead and subtract this 5 over 2x over to the left side. I'm going to go ahead and put it first because my x is written first in my top equation. And then we have our positive y, and that'll equal 1. So now we have it in that standard form that we want to be able to put into our augmented matrix. So I'm going to take my coefficients from my first matrix and my constant, and the same idea from my second matrix or equation. I've got negative 5 over 2, and then 1, and equals 1. So I'm going to go ahead and create my 1 first. At 5, I would like to become a 1. I'm going to multiply by the reciprocal of 5, which is 1/5, to that whole row 1. That means my second row is not going to change, so I'm going to go ahead and rewrite that first. Now that whole first row needs to be multiplied by 1/5. So 1/5 times 5, there's that 1 we wanted. 1/5 times negative 2, so we've got a fraction here, negative 2 over 5. And then 1/5 times negative 7, so negative 7 over 5. So we've created our 1, which is what we want. The next step in our column, we want to make this negative 5 over 2 a 0. The only way we create zeros is multiplying the 1 in the column by the opposite. The opposite would be a positive 5 over 2. And I need to multiply that to row 1 because that's where my 1 is. And then I'll add that to row 2 and it will eliminate that. So remember, we're changing row 2, not row 1. So I'm going to rewrite row 1. And then I'm going to multiply to help me eliminate. So I'm going to multiply this first row by 5 over 2. Well, 5 over 2 times 1 is 5 over 2. 5 over 2 times negative 2/5, well, those are reciprocals and 1 is a negative, so that's going to be a negative 1. 5 over 2 times 7, negative 7/5, the 5s will divide out, 1 in the numerator, 1 in the denominator, and that's going to leave me with a negative 7 over 2. So I need to take those values, I needed to combine them with my second row. So 5 over 2 plus negative 5 over 2, 0, that's what I wanted. Negative 1 plus 1, that's also a 0, so I'm kind of looking like the same kind of answer we got on B, but what will I get in this last spot? So negative 7/2 plus 1, so that would be really adding 2 over 2, which would give us negative 5 over 2. So in this case, we had a similar situation where our variable has eliminated, but now we're left with this statement that -5/2 is equal to 0, which is not true, which means there is no values for x and y that will make this these two intersect. So these two systems do not intersect, these two lines. So watch for these in your matrices. If you end up with zeros, if it equals a 0, you have infinitely many solutions, but if it equals something else, then it's going to have to be no solution. So go ahead and self-assess. How do you feel about solving these augmented matrices using our row operations? And good luck on your assignment.